In 1997, hydrophones operated by the National Oceanic and Atmospheric Administration picked up an ultra-low frequency sound from the South Pacific. It was so loud, it registered on sensors over 5,000 kilometers apart. Researchers called it the bloop. The audio profile showed rapid variations in pitch, a pattern typical of marine animals. Because of the sheer volume required to travel that distance, scientists hypothesized the source could be a creature significantly larger than a blue whale. But the true source was geological. The hydrophones had actually captured a massive Antarctic icequake. An immense block of glacial ice had fractured and collapsed into the sea, generating a sound wave that traveled vast distances through deep ocean acoustic channels. The fact that the scientific community seriously weighed the existence of a giant sea monster demonstrates the scale of our ignorance. Even today, 95% of the ocean floor remains entirely unseen by human eyes. Because it is so remote and unmapped, we often treat the deep ocean as an empty void, out of sight and largely out of mind. Yet, resting quietly in that darkness are vast fields of polymetallic nodules, lumpy, potato-sized rocks containing dense concentrations of minerals like cobalt, nickel, and manganese. These specific elements are highly sought after right now. Global demand is surging to support the terrestrial shift to renewable energy, particularly for the manufacturing of electric vehicle batteries. This creates a direct contradiction in our environmental policy. To secure our surface-level climate goals, industrial operations are preparing to initiate deep-sea mining, strip mining an ecosystem we haven't even finished mapping. If we plunge down into the abyssal zones, thousands of meters below the surface, we find an environment defined by crushing pressure and absolute darkness. Surviving here requires highly specialized biological adaptations. Take the ceratioidae, commonly known as the deep-sea anglerfish. In this vast, pitch-black water, the statistical probability of a male and female encountering each other is nearly zero. To solve this, they utilize sexual parasitism. When a tiny male finally locates a giant female, he bites into her flesh and permanently, physically fuses with her body. Their circulatory systems merge into one. For this to work without the female's body rejecting the foreign tissue, the male actually has to jettison its own adaptive immune genes. Other species respond to these harsh realities through deep-sea gigantism, like the Bathynomus jamesi, a pale, heavily segmented isopod that grows far larger than its shallow-water relatives to maximize energy efficiency. These organisms are not spooky oddities. They are highly specialized biological machines. Their traits took millions of years of stable conditions to evolve, meaning they cannot quickly adapt to sudden environmental changes. Because sunlight doesn't reach the abyss, the food web relies on a different energy source. Chemosynthetic microbes process the toxic, superheated phodids venting from fissures in the ocean floor, forming the foundation of life down here. These exact same microbes, along with sponges and corals, attach to the hard surfaces of the polymetallic nodules, the very rocks the mining industry intends to harvest. Removing those nodules means removing the only solid foundation available for these ecosystems. This habitat operates on a timeline far outside human experience. These nodules accumulate at a rate of mere millimeters per million years. The proposed mechanics of deep-sea mining involve lowering massive, remote-controlled crawler vehicles to the seabed. These machines will crawl across the ocean floor, physically grinding and crushing the rock to separate the metals. The destruction extends far beyond the tracks. The extraction process kicks up a massive cloud of sediment that drifts outward, blocking the faint bioluminescence organisms use to communicate and choking the gills of stationary filter-feeding animals miles away. When you mechanically obliterate a habitat that takes millions of years to form, the resulting ecosystem collapse cannot recover on any human timescale. This scale of disruption brings up a critical legal problem. Who exactly is responsible for protecting and regulating the exploitation of international waters? That duty falls to the International Seabed Authority, an independent organization established under the United Nations Convention on the Law of the Sea. However, the regulatory framework is dangerously incomplete. The ISA's official mining code is still only in draft form, leaving critical questions regarding legal liability and baseline environmental protections completely unresolved. More concerning is the lack of foundational science required to write those laws in the first place. We do not have independent life cycle analyses of the carbon emissions produced by the mining process, nor do we know how far these destructive sediment plumes will spread. The legal frameworks meant to govern the deep ocean are vastly underprepared for the industrial operations currently pushing to exploit it. Humanity is currently weighing a set of known, short-term economic rewards for the battery industry against biological costs we cannot yet measure. The risk is that mining the seafloor for green energy might actually worsen our climate trajectory. Agitating deep ocean sediments risks disrupting the microbial carbon cycle and could significantly alter regional ocean acidification. The deep ocean operates as a specialized biological engine, sustaining the carbon cycles that regulate life across the globe. It is a living system, far more complex than a simple mineral deposit. As we attempt to engineer our way out of a climate crisis on the surface, the only scientifically defensible move is to invoke the precautionary principle. Until we truly understand the deep sea, we must leave it alone.